Hello and congratulations on making it to the bonus tutorial today, where we are going to talk about deep learning techniques applied to our climate emulator problem. So we already worked with some simpler machine learning models to try to solve this emulation problem, but when you're trying to model a complex relationship between inputs and outputs, for example, past temperature and climate variables plus emissions into future climate variables, the complexity of that relationship means that you might need to use a more complex model that has the capacity to capture the maybe nonlinear or non-trivial relationships between the inputs and outputs. And so a lot of modern work on climate emulator models uses deep neural networks, and so that's what we're going to be talking about. That's what the field of deep learning uses to build machine learning models. And if you're interested in learning more about deep learning, you can check out the Neuromatch Academy course on deep learning. It's a course just like this one that gives you background into all different types of deep learning models. So what is deep learning? Deep learning, as I said, is when you build a deep neural network, an artificial neural network, to solve some sort of task. And so the way that artificial neural networks work is that you have inputs that you give to the model. So in our case, again, past climate variables and emission scenarios. And then the model has these layers of artificial neurons. And so these artificial neurons are meant to work in the same way that real neurons do, roughly, which is that they get a weighted sum of their input and they apply some sort of nonlinearity to it. So this artificial neuron in this hidden layer gets an input, gets some weighted sum from the input, so it learns some combination of the inputs that are given to the network, and then it gets some sort of nonlinearity passed through that weighted sum. So this could be a simple rectification where all values less than 0 are set to 0. And then the next layer of artificial neurons gets input from that layer before. So we have an output from each artificial neuron, and that serves as input to the next layer of artificial neurons until eventually we have our outputs where we're trying to create units that produce what we want to produce, such as future climate variables. And what you have to do to make this network work is that you have to train it. And to do that, we use the backpropagation algorithm. So the goal of the backpropagation algorithm is to tell you what these weight values should be. When an individual neuron is combining its inputs, how should it weigh each of them? So how do we know what numbers to put as those weights and those variables in the network? And the backpropagation algorithm is just a way of doing that, where you get to say, this is the desired output I want the model to have, and through calculus you can figure out exactly what the weights of the intervening connections between neurons should be. So we use backpropagation trained on a bunch of data to fit this complex model in order to capture a complex relationship. Now, when you're talking about deep learning and these neural networks, a big thing you have to know about is the architecture of the model. So the architecture refers to things like the number of those artificial neurons, the exact type of nonlinearity that they use, if there's any restrictions on how they can connect to each other, or any added complexity to how they're allowed to interact with each other. These are all details of the architecture. You can also think about how deep the network is. So we call it deep learning because you have multiple of these hidden layers in between the input and output. That's part of the architecture as well. So the architecture just defines the overall structure of the neural network, and different architectures are well suited to solving different types of problems. So whenever you're dealing with a deep learning problem, you need to understand what type of data you have, what type of problem you're going to solve, and that's going to inform what type of architecture you use. So what do we have here? Well, in our case, we have a spatiotemporal problem. So in the climate bench data set, we have these values that represent both past climate variables as well as current and future emission scenarios. And these values have a spatiotemporal layout, meaning that we have different values for different locations in space, different locations on the grid that represents the Earth, as we can see here. And there's a temporal component to this data. So we have values over many different years. And so this kind of spatial temporal format of the data lends itself to certain types of artificial neural network architectures that will be best suited for handling both the spatial and the temporal dimension of this data. So when we think about these building blocks in terms of what types of artificial neural networks can do different things, we have what's called a CNN, or convolutional neural network, that it can help us process spatial data, and we have an LSTM, which is a type of recurrent neural network that can help us process temporal data. And so we're going to break down what each of these different architectures are like and why they're well suited for their specific data types, and then we'll see how they can be stitched together for our problem. So the core idea of a convolutional neural network, this is a type of neural network architecture where instead of just letting any of the inputs connect to any of the hidden layers, there's a constraint where each output neuron only gets input from a subset of the input numbers, input values, and you can see here that they're actually applying this same filter of weights to each location in the input image. So if this was something that represented temperature across the globe at a certain year, to get the activity of the artificial neuron in the next layer, you would apply these values where you multiply each number with its location in the input image and then add them all up, and that gives you the value of the output for the next layer. And what you're doing here really by applying this same filter at all the different locations in the input image is that you are looking for certain patterns in the input image. So this filter, or sometimes called a kernel, a set of weights, this defines a pattern that you're looking for. And when the input data aligns with what this weight describes, then you'll get a high value in the output. And when it's very different from what this pattern of weights describes, you'll get a low value. So you can do this kind of pattern recognition where you're looking for spatial patterns in the data, and you look for the same pattern across the whole image. And then by having multiple of these kernels where you create multiple different outputs, you can look for multiple different patterns. And so in a convolutional neural network, you have multiple of these convolutional filters or kernels, and they get applied to the input, and then that produces different outputs that represent the location of different patterns in the input. And so that's the core operation that's used in these convolutional neural networks to help identify spatial patterns. For the temporal component of our data, we're going to use a type of recurrent neural network. So what we've seen so far in these neural networks are just feed-forward neural networks where you have activity at one layer and it feeds into the next layer and so on. But those models don't have any sort of temporal dynamics to them. A recurrent neural network is a network where the architecture is such that there is some sort of loop in the connectivity, meaning that a neuron's activity at one point in time can propagate through the network and eventually have an impact back on itself. So in this diagram here, we're just showing a single neuron that gets a feed-forward input, but then it also has a connection to itself. And the reason that that's useful for understanding temporal dynamics is that if you had an example neuron like this that, let's say, was getting positive input from the layer below and also had a positive recurrent connection, so that each time step it takes input from the layer below, but it also takes an input from its own past activity, then you could see something like this, where first we get a positive input from the layer below. At the next time step, we're getting positive input from the layer below plus its own past input, and so on and so on and so on. And this allows the artificial neurons to have a form of memory and to integrate information over time. If we didn't have this recurrent connection, there'd be no ramp up. We would just get the same input at each point in time from the feed-forward connection, and we would have no ability to integrate information across time. So recurrent neural networks allow you to integrate information across time and also identify temporal patterns by doing that. Now, the specific type of recurrent neural network that we're working with is called a long short-term memory network. The basic concept is still the same. It's the idea that you have artificial neurons that somehow form loops and you get to have memory. The main difference is that these LSTM artificial neurons, they just have a little bit more complexity inside the neuron itself. They're not just doing a simple weighted sum of inputs to produce an output. They have things called gates inside that allow that individual unit to hold on to information for longer, which makes them extra good at identifying temporal patterns that are spread out over time. So that is the type of recurrent neural network that we're using. So how does this all fit together? Well, when we want to be able to predict future climate variables, we have to pass in our past climate variables. So at each time step in this model, the information that we have about past weather for a given year, plus information that we have about emission scenarios, which also have a spatial component, that gets fed into the convolutional neural network. So it's looking for patterns at one point in time for those spatial data, and then the output of that convolutional neural network, where we've identified certain features that we might care about, those are passed into the LSTM. So at each point in time, we pass spatial data through the CNN, and that gets passed into the LSTM at each point in time, where the LSTM is allowed to hold on to that information over time and identify temporal patterns. And eventually, we use the activity at the last time step of the LSTM, and we project it back into the spatial dimension to produce a prediction of future climate variables. And to do all of this, you're going to use PyTorch, which is a very common deep learning software library that's used across academia and industry. It has a lot of built-in tools for building these exact types of networks. So just to summarize, you'll still be working with the Climate Bench dataset. You'll be using the full spatial temporal extent of it. Previously, we were using a restricted version of the Climate Bench dataset. And to get started with this, you'll have to first load and store that data in a way that allows PyTorch to access the spatial and temporal components of it. And then once you've loaded that data, you will define the model architecture, this CNN plus LSTM. You will train the model. Here we have the same considerations about having a training data set and then a separate testing data set, and then you will analyze the results. So I hope you enjoy tackling this more advanced way of building a climate model emulator.